In section 14.1, we saw that the water molecule can act both as a proton donor, an acid, and as a proton acceptor, a base. In the presence of an acid, water behaves as a base, whereas in the presence of a base, water behaves as an acid. It's not surprising, therefore, that in pure water, one atom molecule can donate a proton to another water molecule in a reaction in which water acts as both an acid and a base in the same reaction. Called the dissociation of water, this reaction is characterized by the equilibrium equation Kw equals H3O plus times OH minus, where the equilibrium constant Kw is called the ion product constant for water. As discussed in 13.5, the concentration of water is omitted from the equilibrium constant expression because water is a pure liquid. There are two important aspects of the dynamic equilibrium in the dissociation of water. First, the forward and reverse reactions are rapid. H2O molecules, H3O plus ions, and OH minus ions continually interconvert as protons transfer quickly from one species to another. Second, the position of the equilibrium lies far to the left. At any given instant, only a tiny fraction of the water molecules are dissociated into H3O plus and OH minus ions. The vast majority of the H2O molecules are undissociated. We can calculate the extent of the dissociation of water molecules from the experimental measurements that show the H3O plus concentration in pure water to be 1 times 10 to the negative 7th m at 25 degrees Celsius. Since the dissociation of the reaction of water produces equal concentrations of H3O plus and OH minus ions, the OH minus concentration in pure water is also 1 times 10 to the negative 7th molar at 25 degrees. Furthermore, we know that molar concentration of pure water, calculated from its density and molar mass, is 55.4 m at 25 degrees. From these facts, we conclude the ratio of dissociated to undissociated water molecules is about 2 in 10 to the 9th, a very small number indeed. In addition, we can calculate the numerical value of K at 25 degrees is 1 times 10 to the negative 14th. In very dilute solutions, the water is almost a pure liquid and is a product of H3O plus and OH minus concentrations, is unaffected by the presence of solutes. This is not true in more concentrated solutions, but we'll neglect the complication and assume that the product of H3O plus and OH minus concentration is always 1 times 10 to the negative 14th at 25 degrees in any aqueous solution. We can distinguish acetic, neutral, and basic aqueous solutions by the relative values of H3O plus and OH minus concentrations. In acetic, H3O plus will be more than OH minus. In neutral, they'll be equal, and in basic, H3O plus will be less than OH minus. At 25 degrees, H3O plus is more than 1 times 10 to the negative 7th in an acetic solution. H3O plus equals OH minus, which equals 1 times 10 to the negative 7th in a neutral solution. And H3O plus is less than 1 times 10 to the negative 7th in a basic solution. If one of the concentrations, H3O plus or OH, is known, the other is readily calculated. In the previous discussion, we were careful to emphasize that the value of Kw equals 1 times 10 to the negative 14th applies only at 25 degrees. That is, the Kw, like all the equilibrium constants, is affected by temperature, and the H3O plus and OH minus concentrations in neutral aqueous solutions at temperatures other than 25 degrees deviate from 1 times 10 to the negative 7th m. Unless otherwise indicated, we'll always assume temperature is 25 degrees. Rather than write hydronium ion concentrations in molarity, it's more convenient to express them as logarithmic scale known as the pH scale. The term pH is derived from French puissance de hydrogen, power of hydrogen, and refers to the power of 10, the exponent, used to express the molar H3O plus concentration. The pH of a solution is defined as the negative base 10 logarithm of the molar hydronium ion concentration. So pH equals negative log H3O, or H3O equals antilog negative pH, which equals 10 to the negative pH. Thus, an acetic solution having H3O plus equals 10 to the negative 7th m has a pH of 2. A basic solution having an OH minus equals 10 to the negative 2m, and an H3O plus equals 10 to the negative 12th m has a pH of 12, and a neutral solution has a pH of 7. Note that we can take the log of H3O plus because H3O is a dimensionless ratio of the actual concentration to the concentration 1m in the standard state. Although much less frequently used than pH, a POH can be defined in the same way as pH and used to express the molar OH minus concentration. Just as pH equals negative log H3O plus, so POH equals negative log OH minus. It follows from the equation H3O plus times OH minus equals 1 times 10 to the negative 14th that pH plus POH equals 14. If you use a calculator to find pH from the H3O plus concentration, your answer will have more decimal places than the proper number of significant figures. For example, the pH of the lemon juice in worked example 14.4, H3O plus equals 2.5 times 10 to the negative third, is found on a calculator to be pH equals negative log 2.5 times 10 to the negative third equals 2.60206. This result should be rounded to pH 2.6, two significant figures, because H3O plus has only two significant figures. Note that the only significant figures in the logarithm are digits to the right of the decimal point. The number to the left of the decimal point is an exact number related to the integral power of 10 in the exponential expression for H3O plus. Because the pH scale is logarithmic, the pH changes by 1 unit when H3O plus changes by a factor of 10, by 2 units when H3O changes by a factor of 100, and by 6 units when H3O changes by a factor of 1 million. To appreciate the extent to which the pH scale is a compression of the H3O plus scale, compare the amounts of 12 molar HCl required to change the pH of the water in a background swimming pool. Only about 100 milliliters of 12 molar HCl is needed to change the pH from 7 to 6, but a 10,000 liter truckload of 12 molar HCl is needed to change the pH from 7 to 1. The pH scale and pH values for some of the common substances are known in figure 14.4. Because the pH is the negative log of H3O plus, the pH decreases as H3O increases. Thus, when H3O plus increases from 10 to the negative 7th m from 10 to the negative 6th m, the pH decreases from 7 to 6. At 25 degrees Celsius, acetic solutions have a pH less than 7 and a basic solution have pH greater than 7.